All right, guys, we are live. If you guys want to find the live stream, you can, but you are seeing it even more live. No, it's on YouTube. YouTube. It's from the NDHS Physics channel. Yes. You guys are live now. NDHS Physics. You guys are live. Huh? All right, guys, we are going to take notes. Today we are talking about Newton's first law. We talked about it a little bit last time. Do you guys remember we said it is the same as the law of inertia? Okay. So I've written it up on the board. And I think last time we talked a little bit about what inertia was, right? Yeah. So the law of inertia is pretty much the definition of inertia. What we have going on here, we're going to use the cart that we used for our demonstration the other day, is the whole idea of what inertia is. So here, we've got a cart. If I leave it alone on the track, do you expect it to start moving? No, we expect it to stay still, right? This is the objects at rest tend to stay at rest part. Good? Okay. Now, if we push on this, even if we push on it pretty slow, does it stop immediately when I let go of it? No? So this is our objects in motion tend to stay in motion. But this does eventually stop, right? See, it didn't even reach the end of the track. Why does it stop? The track is slightly slanted. So, yeah. Now it's rolling backwards. Why would it be rolling backward? Anybody have any idea?
It's slanted gravity.
Okay, so it's slanted, so gravity is actually pushing on it slightly. Why did it slow down?
Friction.
Okay, friction. So friction is that outside force, or in this case, when it stopped and turned around and started rolling back this way, that's gravity acting on it. Okay, so we have that outside force acting on our object. Good? Now, especially the whole objects in motion, objects at rest stay at rest, that is very much a thing that we just know, right? We would be very surprised if any of the objects on my desk just suddenly started moving, right? Yeah? Okay? You guys were very surprised when the cart just suddenly started rolling backwards, right? Okay? That's not what we expect to happen. The objects in motion stay in motion one, though, is not something that we see super often because we have things like air resistance and friction that affect everything. We throw a ball through the air, it's got air resistance, right? Yeah. We roll a ball along the ground. We've got friction and air resistance. We roll a cart, right? It's got friction, it's got air resistance. So there, we do have outside forces. So it's really hard for us to have a situation where we don't have those outside forces. Good? Now, if we could go to space, right? And we could put, say, I don't know, a tennis ball just floating in space. And then we poke it, okay? We don't even have to push it hard. That tennis ball is going to keep going pretty much forever. Now, once it runs into like a planet or another gravitational field or an asteroid or something like that, obviously we're going to get that outside force and it's going to change direction. But if it doesn't run into any of that stuff, it's going to keep going forever and ever and never slow down, never change direction. Cool? Okay. Now, one thing about inertia that this doesn't explicitly say is the more mass an object has, the more inertia it's going to have. Okay? The more resistance to change in motion it's going to have. So if you think about it, if we have something that's really, really big, okay? So maybe like a giant box that's full of lead. Really big, really heavy, lots of mass, right? Yeah? Is that going to be very easy to move? No? Even if we had some sort of magical thing that would cover it above the ground so we wouldn't have much friction with it, it would still be very, very difficult to get it to move quickly. Okay, now could we? Yes, especially if we don't have friction. We could move it, but it's going to be a lot harder to move than, let's say, the same size box full of ping pong balls, right? Ping pong balls are mostly air, they're very light. So a box full of ping pong balls can be a lot easier to move than one full of lead. Good? Does that make sense? Same thing goes with stopping it. The more mass you have, the more inertia you have, the harder it is to change that motion. Any force applied will change that motion, but it's just not going to change it as much. Does that make sense? Okay. So this is Newton's first law. Newton's first law kind of lays the groundwork for the next ones. Okay. Newton's second law is actually the equation that gives us a little bit more information about what's going on here. Okay, so this just says, hey, if we've got something with mass and it's not got any forces acting on it, it's going to stay there or it's going to keep moving just like it is. Good? Okay. Newton's second law doesn't have a fancy nickname like this one. Bless you. Newton's second law is most commonly stated as an equation. Okay, it's really nice shorthand. Writing it out takes about a paragraph. Putting it in equation form is 3 letters. Okay, my guess is, like you guys, when you're texting, you'd probably rather write down 3 letters than an entire paragraph, right? Okay. So Newton's second law can be very conveniently summed up into force equals mass times acceleration. Okay. This is the way you learned it in grade school, if you did learn it in grade school. This is the way you will see it pretty much anywhere you look for it. But since you guys are now in high school, I do want to make a little bit of an addition here. Okay? We're going to put something a little bit more precise here than just force. We're going to put F sub net, or F net, or the net force acting on your object. Okay? We mentioned net force a little bit when we were talking about vector addition. The net force is the vector sum of all forces acting on an object. The net force is the vector sum of all forces acting on an object. Okay, so this is going to be a vector quantity. Essentially what it's looking at is, instead of just saying, hey, I've got one force acting on this object, so therefore it's going to accelerate like this, it accounts for all the forces acting on it. Okay? So if we take maybe this Christmas ornament, and we are looking at a really simple problem, I'm just pushing on it like this, this would work without the net force, right? But if we really want to know what's going on here, you'll notice that as I try and push it up higher, right, it falls back down. Yeah? So here, my finger is not the only force acting on it, right? What's another force acting on it? Is gravity acting on it? Okay. Is the string applying a force to it? Okay. There's several other forces acting on it. Okay. So you'll notice that when I push on it, it doesn't go straight forward. The string pulls it upward. So it kind of moves in a circle, and then gravity wants to push it back the other way. So if we really want to look at what's actually happening with that Christmas ornament, we have to look at all of the forces acting on it. Good? Okay. This also says, if we have a situation, we'll go back to the Christmas ornament. Actually, let's go to the other one because the other one's not moving. That'll work better. So here, we have a Christmas ornament. It's pretty stationary, right? Yeah, not moving. Okay. There are forces acting on this Christmas ornament, right? Yeah. Gravity is still acting on it, even though it's not moving, right? But we can actually use F equals ma the other way and say, hey, we know gravity has to be acting on here, but can there be a net force since it's not accelerating? Is that accelerating? It's not accelerating. So we can actually go back and do this backwards and say, okay, my acceleration here is 0. That means this whole side of the equation is 0. My net force has to also be 0. Now, it doesn't mean there's no forces acting on it. We already talked about that. Gravity is pulling the Christmas ornament down. But what this means is the string that's holding the Christmas ornament up has to apply a force in the opposite direction. Does that kind of make sense? Okay. So there's several different ways we can use this equation. It is very, very useful. And like I said, this kind of ties into the first one. You remember how we were talking about if something has a lot more mass, it's going to be harder to accelerate? Yeah. This actually tells you how much harder. Okay. Notice that the mass does show up in this equation. So if we apply a force, okay, our amount of acceleration has to do with our mass. Okay. We can actually solve this several different ways. This is the most famous form of this equation, but your book actually doesn't write it this way. So if you went and looked in your book, they have it solved for acceleration. So to solve for acceleration, we're going to divide both sides by m. And so you'll see F net over m equals a. Good? So, just to kind of show you guys how this works, let's say that we have a box. We'll start fairly simple. So we have a box. Let's say that this box has a mass of 10 kilograms, and we are applying one single force to it of 1 Newton. Okay, we're going to pretend that gravity doesn't exist for this one, so we can just deal with one force to start out. Good? Okay. So we've got 1 Newton going that way. We've got a 10 kilogram box. Can we calculate the acceleration? We can, right? So here, this is our force. So we're going to put 1 Newton in for F net. We don't have any other forces, so we don't really have a sum here. And then we've got 10 kilograms for our mass. Good? All right, so here, 1 over 10 is 1/10. So we get 0.1, right? Everybody good? All right. What units do we have? Any ideas? What units would we expect to get for acceleration? Meters per second squared. How do we get that from newtons divided by kilograms? Any ideas? Hint, newton's a derived unit. What was different about derived units? Do you guys remember? Derived units were the ones that were made up of other units. Okay? So a newton is actually a kilogram times meters over seconds squared. Okay, so if we take kilograms times meters over seconds squared and divide it by kilograms, what's going to happen? The kilograms are going to cancel out, and then we're conveniently left with meters per second squared, the units that we should get, right? Does that kind of make sense? Yeah. All right, so we've now used this once, but I want to try something else. Let's say that we then come and we add a whole bunch of stuff to this box. So instead of being 10 kilograms, it's now 100 kilograms. Do you think our acceleration that we get from 1 Newton is going to be bigger or smaller? Okay, it would make sense that it would be smaller, right? Because you've got a heavy thing, you're still just pushing on it with a very small force. 1 Newton is a pretty small force, okay? So you're pushing on it with a pretty small force. We would expect this to have a much smaller acceleration than a much smaller box, right? Make sense? Okay. So let's see what happens. So we still have our 1 Newton as our force, but this time we have 100 kilograms instead of 10. What's 1 divided by 100? 1/100. So we get 0.01 meters per second squared. Okay? So this is going to be one of our inverse relationships. You remember that name from our graph? Okay? As the mass gets bigger, our acceleration gets smaller. Good? As the mass gets bigger, the acceleration gets smaller. And this is exactly what we would expect from that first law when we talked about inertia, right? Do you guys remember that? Okay. All right. Do you guys have any questions on this? Yeah.
What did you say about the net force?
The net force is the sum, the vector sum of all of the forces acting on the object. I don't want to get into that too much right now because I just want to introduce the laws. So that's why we're keeping it to one force. But yeah, it's the vector sum of all of the forces. Any other questions? No? All right. This is eventually going to lead to us talking about free body diagrams and stuff. We're not going to do a whole lot of that this, I guess, semester, because next week starts finals. So we're not going to do a whole lot between now and then. I just want you guys to know how to use the basics of Newton's laws. Good? Okay. Any questions on the second law? You guys ready to go on to the third law? Okay. All right, Newton's third law. Anybody know which one's left? Okay. This one's the weird one. This is the one that probably is the most confusing for most people. Okay. Every action, every force, so action here kind of stands in for force, has an equal and opposite reaction force. Okay. So a lot of times this is talked about in terms of if I come over here and I push on the wall then pushes back on me. Okay. Sometimes that gets a little bit confusing because if the wall is pushing me, why am I not being pushed back from the wall? Okay. more of what's going on here is I'm pushing on the wall, and the wall is pushing back in such a way that the wall's not falling over. Does that kind of make sense? My hand's not going through the wall. We have the same thing happening when we have something sitting on a surface. So if we take the dice and we put it on my desk, right? Gravity is still working on the dice, right? So the dice has a weight. The weight is pushing down on my desk. My desk is pushing back up, and we know that because the dice doesn't fall through my desk. Make sense? Okay. A lot of times people get into this misconception that because something has to push back, you can't ever push on something enough to move it. Okay? Because if you push, say, actually, let's use a piece of paper. If we push on this piece of paper, right? Can I push on this very, very hard before it moves? No, it's a piece of paper. It can't support much weight, okay? So if I push on it, it moves out of the way. I can only put as much force on this piece of paper as the paper can push back with. Does that kind of make sense? Once it starts to move, those forces that I'm applying directly to the paper and the paper is applying back to me are equal and will remain equal. But this doesn't mean that we can't have motion. We can clearly see that the paper is moving, right? What happens is the forces other than those two equal and opposite ones come into play there. My body, right, is not moving because the force that the paper is exerting on my body as a whole is smaller than the force that I'm holding the paper with at the top, or my feet and the friction on the floor is exerting back on me, right? So I'm not going to move. But the paper itself can't resist that force that I'm applying to it. Does that kind of make sense? Yeah? That's why here, if we start talking about with the cart, I can obviously move the cart, right? The force that I apply to the cart is the same as the force that applies to me from the cart. But when I push on here, the cart's not the only force acting on me, right? Are there other forces acting on me? Okay. Gravity is obviously acting on me. Just as a hint, when we start talking about free body diagrams or forces or things like that, gravity is always a good place to start. Because gravity is pretty much always acting on anyone that's not floating in space. Good? Okay. So, got gravity acting on me. I also am standing on the ground, right? There's going to be friction forces between my feet and the ground. So even though I'm not moving, when I apply the force to the cart, right, I'm actually getting that force, sort of, from the friction between my feet and the floor. So my net force on my body is still going to be 0. Does that kind of make sense? That's why the cart moves and I don't. So I have a net force of 0. The cart, since it's moving, obviously doesn't have a net force of 0 then, okay? My force that I push on it with is bigger than the friction force between the wheel and the cart. Does that make sense? You guys have any questions on that? No? All right. The bell's about to ring, so I'm not going to go any farther. Have a good day, guys. Was it one of you guys